Okay, today we're going to talk about section 7.1. Section 7.1 is inverse trig functions. And before we all get up and start leaving the room, let's just take a second and let's focus on this. 7.1. 7.1 is the first section in chapter 7. We've never been overwhelmed by anything that Michael has given us in our book in section 1 of any chapter. Yada, 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 yada. It's all going to be okay. So functions, trig functions, right? Trig functions. Let's just take a quick look at what a trig function does. A trig function, like every function, has a domain, has a range, and a trig function maps from the domain to the range. So this is our domain. This is our range. Now, did you notice, or have you paid attention to, or has it become obvious to you, or did it just go right by you? Did you notice what trig functions do? Trig functions, they change the character of the domain element and the range element. Trig functions start with angles, like 30 degrees or pi over 3 or 5 pi over 4. They start with angles and they turn angles into numbers. That's what trig functions do. They change the character of what you're working with. We don't have a lot of experience in our interaction with functions where they completely change the character of the domain element when they generate the range element. But trig functions start with angles and turn them into numbers. Well, we know from our past experience with functions and their inverses, we know what an inverse trig function then is going to do. Inverse trig functions go this direction. This is the direction that an inverse trig function goes. We've said in our past experiences that inverse functions take what the function called the range, treat it as its domain, and then map it back onto what the original function called the domain, which of course is now the range of the inverse function. So what's important from this picture? What's important from this picture is trig functions are kind of interesting in that they change the character of their domain element into a completely different type of item. They turn it into a number. Angles aren't numbers. Angles measure angles. Numbers are numbers. We count with those. Inverse trig functions go the other direction. Okay? Inverse trig functions go the other direction. So if we're going to learn about inverse trig functions, we're always going to do this with the idea in the back of our mind that this is section 7.1, right? It can't be that bad. It can't be that bad. So let's just write down a problem and see what happens, right? Let's just write down a question. A question that we're going to encounter is going to be something that looks like this. This is an inverse trig problem. It's sine inverse, right? And so for the inverse, we put the little -1 up there. Of course, that's not the power. It's our indication that that's an inverse function. Yeah, I know. They could have come up with a better symbol because it looks like a power. But we're us. We know that's not a power. So what does this mean, right? That's what we have to start with. What does this mean? And let's do another one. We'll do another one. We'll do inverse cosine. And we'll do √2/2. Okay. So what we have to understand before we begin is the question we're being asked, right? We can't answer any questions if we don't understand the question itself. And a lot of you experience this maybe in your first day of freshman year when you went to your GATE Spanish class. You spent your whole time in there and she kept asking you questions and you couldn't answer them because you didn't know what she was asking. If we don't know what we're being asked, we can't answer the question. So what is this asking us, right? Well, this is an inverse trig function. Inverse trig functions go backwards. So this is a number. Look, right here, it's a number. So our answer, right? Our answer is going to be an angle. The same is going to happen down here. This is a number. The answer is going to be an angle. So we have to begin with the question, right? We have to begin with the question. And so let's write the question down. This says, what angle has a sine that equals 1/2? That's the question that we're being asked, right? That's the question we're being asked. We have to understand the question. This says, what angle has a cosine that equals √2/2? So the first thing we have to do to understand inverse trig is we have to understand what they're asking us to do. If we don't understand what they're asking us to do, we can't answer the question because we don't know the question, just like back in Spanish. So how are we going to answer the question? Right? What are we going to do? Well, we answer trig questions by writing down a quadrant and writing down referencing. Right? I mean, that's how we answer trig questions. These are trig questions. Quadrant and reference angle has worked so far. Maybe we should stick with that. What angle has a sine that equals 1/2? Okay, that's what it's asking us. What angle has a sine that equals 1/2? Well, we have to find the angle. Now, if this was a regular trig question, right, this would be 1/2 right here. And we'd be looking for this angle over here. And we know something about that process, right? We know to answer that question, we draw the unit circle. We say all students take calculus. We need sine to be positive 1/2. Sine's positive here and here, negative here and here. So for quadrants, we get quadrant 1 and we get quadrant 2. If we were playing the question that we've asked down here, if we were looking at this question, right, √2/2, cosine √2/2, it would be a different answer, wouldn't it? It'd be a different solution. Because for cosine, right, for cosine, we would need a different circle. Let's just draw another circle right here. For cosine, we would be positive here and here, negative here and here. So we would have, for our quadrant, we have quadrant 1 and quadrant 4. So if we just do what we've been doing, we're probably going to get ourselves at least on the path to getting the correct response. Now we need a reference angle. Now we know how to find a reference angle. Right? So let's talk a little bit about how we found these quadrants. Right? Let's just make sure we review. We noticed that this was a plus. Notice I left space in the bracket there. I left space so I could write the plus. That's a plus. And we said, where is sine positive? And we wrote those quadrants down. Here we noticed this was a plus. We said, where is cosine positive? And we wrote those quadrants down. Okay. Now we need a reference angle. Well, how are we going to find a reference angle? Same way we always find a reference angle. We're going to look at this and we're going to say that's sine. Sine is opposite over hypotenuse. And we're going to write down our special triangles over here. Now, I just look for a side that has an opposite side of 1, an angle, pardon me, that has an opposite side of 1 and a hypotenuse of 2. Well, I need an opposite side of 1 and a hypotenuse of 2. That's right here. So my reference angle is going to be pi over 6. Now, we know what to do from here, right? We have a reference angle of pi over 6 in quadrant 1, so that's us right there. So that gives us an answer, pi over 6. But we also have a reference angle of pi over 6 in quadrant 2, that's right here. That gives us an answer of 5 pi over 6. Quadrant 1 and quadrant 2. Now, is there anything else we could do? Could we find any more answers that work? And just lead them until the point that they, somebody typically will say, well, we could have gone backwards. Oh yeah, you're right. You could go backwards. If we go backwards, this is 6 pi over 6 right here because we're in the over 6 world. So now we're at negative 7 pi over 6. And then of course, show them that this is negative 11 pi over 6. I like to do 2 more just to emphasize the point. So I like to show them, we could go all the way, around, right? We could go all the way around to here. And if we did that, this is 12 pi over 6. So we get 13 pi over 6. And of course, if we went all the way around and went over to here, this would be 18 pi over 6. And that would be 17 pi over 6. And then I tell them, look, it's section 7.1. We have a pattern, right? 1, 5, 7, 11, 13, 17. These differ by 4, then this differ by 2, then this differs by 4, then this differs by 2, then this differs by 4, then the next one's going to, maybe that's why it's 7.1, right? Because it's got to be 7.1 for a reason. Play the same game over here, but I use this example to emphasize to them that we've got to be able to unrationalize, because they tend to get stuck on that. They tend to get stuck. They go, well, I don't have a triangle that had a root 2 and a 2. Yes, you do. You have a triangle that has a 1 and a root 2. And so we talk about the fact that this is positive. That's where this comes from. And then for cosine, I always write right here, adjacent over hypotenuse. And then they can look at their triangles. They come up with the adjacent side is 1. The hypotenuse is root 2. So they end up with pi over 4. And then I draw them pi over 4 here, but then of course they also get pi over 4 here. So now we have pi over 4 and we have 7 pi over 4. And then we do our backwards game. We get minus pi over 4. We get minus 7 pi over 4. We do our full rotation game. This of course is 8 pi over 4. So we get to 9 pi over 4. And then we get all the way back around here. So instead of that being 8 pi over 4, it of course turns out to be 16 pi over 4. So we get to 15 pi over 4. And I think I did those right. If I didn't do those right, don't judge me. Numbers are hard for me. So this is when I ask them questions like, well, look, there's a pattern. Maybe that's why it's section 7.1. But is there something about this that seems funky to you? Is there something about this that doesn't seem right? And this is why I talked about, that little voice in your head that, Disney showed us with Jiminy Cricket. That's your conscience, but there's a lot of little voices in your head because you're smart and There's little voices in your head when you're doing a problem in school and you think to yourself, I'm not doing this right. Something about what I'm doing is wrong. I don't know what it is, but I know. So that's where we have that conversation. And then I say, well, what's this word? And what did your Algebra 1 teacher teach you about that word? Your Algebra 1 teacher said this. That's what your Algebra 1 teacher promised you. For every x, there's only one y. That's what your Algebra 1 teacher said. For every x, there's only one y. Now, I doubt they lied to you, because your Algebra 2 teacher told you the same story, and I told you the same story at the beginning of this book. For every x, there's only one y. Yet, we said inverse trig functions turn this into the domain. Right? They treat this as the domain. They treat this as the range. Which means for inverse trig functions, this is x and this is y. So 1/2 is my x, my angle is my y, 1/2 is my x, those are all my y's. And that's when I point out to them, maybe this is what the little voice in your head is talking about. Maybe this is why that little voice in your head is telling you, I don't like this, something about this is wrong. And so from here, this is the first time that I actually draw a trig function. And so I draw sine for them. And I point out that, you know, 1/2 is here. And we have a conversation about what's wrong. All right, what's wrong? This is quadrant 1. This is quadrant 2. Of course, I draw it bigger. And I point out, look, we have 2 answers. And then over here, of course, because it's sine, this is quadrant 1. This is quadrant 2. This is quadrant 3. This is quadrant 4. And I spend a lot of time as we go through trig re-emphasizing to them that on this graph, these are the quadrants. So if you haven't done that, it might be an opportunity to introduce that. And I tell them, look, you get another answer in quadrant 1 and quadrant 2. And that's what we wrote down. So we have the whole conversation here that leads to the idea that the function is supposed to be 1-to-1. Right? What did our algebra teacher tell us about functions that are invertible? What did our algebra teacher tell us we had to have before we can get to an inverse function? And then, and only then, once they've come up with the idea that they're supposed to be 1-to-1, then we have a conversation about somebody, right? The magic somebody decided to slice this. There's a lot of places you can slice it, as you and I both know, and I point that out to them. And I say that somebody decided to slice this right here to make it 1-to-1. And now we only have one answer. And our answer is in quadrant 1. So that allows us to eliminate this, but then that allows us to eliminate this. It allows us to eliminate which one? Now I got to figure out which ones are in quadrant 2, and I'm not that smart. So let's see. -7 pi over 6 goes away. -11 pi over 6 stays. 13 pi over 6 stays. 17 pi over 6 goes away. And I tell them, look, we got rid of half the answers. But we don't get this answer in quadrant 1 because our function is not 1-to-1. And so now we eliminate this answer. And then also we don't get this answer in quadrant 1. And now we only get one answer. And if we look at the graph, this leads me to 1 and 4. And then I do a similar thing down here with cosine, leads me to 1 and 2. And then I don't do a long lecture on tangent. We just talk about the fact that, you know, we draw the graph of tangent. Point out we want it to be 1-to-1, so there's lots of choices. For example, we could choose, this is quadrant 1, of course, this is quadrant 2 right here. We could choose 1 and 2. I mean, we could choose 1 and 2, but we'd have some complications, right? This is 0 there, this is 0 here. So we'd have to eliminate one of those two things, and we would have an asymptote right in the middle of our domain. So that's probably not the best choice. But if we chose 1 and 4, we get 0, 0 in our domain, and we get no asymptotes. So that's how I lead them into tangent is 1 and 4, cosine is 1 and 2, sine is 1 and 4. And then I erase the whole whiteboard, and I'll just write it right here. I write words, but I do this. I do sine is 1 and 4. I do cosine is 1 and 2. And I do tangent is 1 and 4. And I still have I guess I don't erase the whole whiteboard because I still have the graph of of sine, cosine, and tangent on the board. Okay, I still have them on the board, but I get rid of all this other stuff and I call their attention to this, and I ask them specifically to pay attention to these two things. Because if we look at those in first glance, they look to be identical. Right? They look to be the same. Sine is 1 and 4, cosine is 1 and 4. But you and I know what I'm trying to get them to notice. I'm trying to get them, of course, to notice that pi over 2 and negative pi over 2 are not present here, but pi over 2 and pi over 2 are present here. That's why I make those big dots when I do this. I make a big dot. I don't say anything about the dot, but I just make a big dot. And here, of course, I draw asymptotes. And then I try to lead them to the point that somebody notices, because I ask them over and over and over, those really the same? And they're like, yeah, 1 and 4, that's where they start. And then eventually somebody will come up with, wait a minute, those aren't the same. And I ask them to elaborate, and they'll go, well, this one has pi over 2. This one doesn't have pi over 2. And then I make a big deal out of make sure you pay attention to which one has pi over 2 and which one doesn't have pi over 2. All right, there you go. I don't know how long this went, longer than it was supposed to, but hopefully that helps. And if you have any questions, obviously you know where to find me. All right, thanks, Jennifer, for listening. Probably more than my students do.